Let's look at an example that has a current that's flowing from the bottom of the screen here on the left hand side, and then it makes a semicircle arc over through this magnetic field. The magnetic field is pointing into the page. That's think about the back end of an arrow, being the feathers. If it was pointing towards us, it would be just a dot. And then the current goes down the right side of this wire here. So the question that we have is, what is the total force along this wire due to the magnetic field? Well, let's look at just the straight edge here. The straight edge, we know that if we use the right hand rule, we put our fingers in the direction of the current, then bend towards the magnetic field, our force is going to be in the direction towards the left. So that's going to be our force. And if we look at this straight section on the right hand side, we use the right hand rule, fingers going towards the current, then bend towards the magnetic field, our force is going to be towards the right. Now, since these two offset, then we get a cancellation between these two forces. So now let's look at the forces along this ring. Well, let's draw a radius out, and if we use the right hand rule, then the current is point our fingers towards the current, then towards the magnetic field, and our right thumb will head towards the direction of the force, so it's going to go in this direction, and it's going to be perpendicular to that tangent point. So this will be a differential force. And if I go to the exact opposite on the other side, so that this angle is theta and this angle is theta, I'm going to have the same differential force as I had on the other side. Now let's look at the components. My x direction, this is going to be differential force in the x direction, and I'm going to have a differential force y direction, and same here, have y going up and the x going towards the left. So you notice that the x components cancel out, and all we're left with are the y components. So we know that with these cancellations we can simplify our work. So let's write our differential force is equal to I dl cross b. B is a constant, and then if we want the magnitude, that's just going to be I dl, actually this L is a vector, times the field, and then I'm going to have sine of, we'll call it phi, or no, let's call it theta, because that's what the definition we had was theta. And theta is just going to equal 90 degrees, so that leaves me with current times differential length times magnetic field because theta equals 90 degrees. Now my total field, total force is going to equal the force in the y direction, and that's just going to be equal to current times magnetic field times differential length. And now we have to figure out differential length. Well, L is a constant or a function of theta, and that's just equal to r, because no matter what theta is, our value of that is r. And now we can do the differential length in terms of theta in d theta. Well, actually, we can use our definition that we had before from the previous slides. We had differential length, we get to it the other way if we did it, is equal to the square root of r squared plus dr over d theta squared times d theta. And notice that this this differential goes away because r is not in terms of theta, and then we just are left with r squared square root, so our differential length is equal to r d theta. So now we can make our force, differential force is equal to I times B times R d theta. And remember that because it's in the y direction, this is where I forgot to put, we have a sign up here, sine theta, because it's in the y direction. This sign is not from the cross product. It's from the y component. Now we're ready, we can make an integral. So we'll have an integral, that'll make this equal to f, 0 to pi. Now we are going to integrate from this side back against the current. The reason why we can do that is because we've already defined the cross product and the direction of the forces. And so now we get I, B, R sine theta d theta. Well, I, B, and R are just constants, and then I'd have the integral of sine theta d theta, so that's going to be negative I, B, R cosine theta, and I just put the negative sign outside. This goes with the cosine. That's where the negative comes from pi to 0, and that equals negative I, B, R cosine pi minus cosine 1. I'm sorry, 0. and that's just equal to, well, cosine of pi is minus 1 minus cosine of 0, which is 1. So that's going to be a negative 2. And with the negative, it's 2IB R. That's our formula for our force due to this current flowing through this wire.